Alright, welcome back. It's time for examples of maximums, minimums, critical numbers, and all the calculations behind them. It's not super complex. We're going to start off with this example right here. It's just a graph that I drew beforehand. We have our y-axis and our x-axis, and I've labeled the x-axis just so I can help you identify the points. So, when I ask you to find all the local minimums and maximums as well as the absolute minimum and maximum, then I'm asking you to find the x value of it. But if I say I want you to find specifically the value of the maximum or the minimum, I'm talking about the y value. So if the question says find the value, it's not asking for the x value, though you're going to have to find it. It's asking for the y value of that x corresponding. So, oh, I missed a part on the graph. There's a hole right here. Okay, easy. Anyways, so where is the absolute maximum? We're going to look at the x values right now. Absolute max, absolute min. So, where is the highest point on the graph? Well, it's obviously right here. So, let's switch over to blue. Just go straight down, and looks like that value is 4. So x equals 4. Now, where's the absolute minimum? Well, the lowest point on the graph appears to be right here. Problem is, this is not a defined point, so it can't actually find its minimum. And you would think that, oh, it should be x equals 7 or just before it, because I mean the value that's closest to 7 but that isn't actually 7 is still a minimum value, and no, because it has to be a limit, and that point doesn't exist, therefore it is not a minimum or maximum. So the absolute minimum does not exist for this function. This is a piecewise function, by the way. It's got some jumps in there. So let's talk now about the locals. And so local maxes and minimums. So we can say that one local is going to be right here. Here's a local maximum, and right here is another local maximum, and right here is another local maximum, but at the point that it's defined. So we have 3 local maximums, 1, 4, and 6. X equals 1, 4, 6. Minimums, well, let me change color for this one. Let's go to green. We have 1 at 2, and we have 1 at 5. And we would have had 1 at 7, but 1, it's an endpoint, and you can't have a local there, and it's undefined anyways. So we have 2 and 5. So x equals 2 and 5. Now, if I wanted to find the values of these maximums and minimums, like if I said, so what is the highest value on the function, I would take the original function, let's say like y equals 5x to the 4th minus 3x cubed. What I would do is I would just plug my value back in. For example, 4, it would be 4 to the 4th minus 3, 4 cubed. And what that would give me is, since it's the absolute maximum, it would just give me the y value at this coordinate. And that's how you find the value of it. You just plug these numbers back in. Now let's shift away from graphs and start looking at equations, or just functions. So when you are given a function you aren't given a graph, you have to resort to using critical numbers. On a graph, it's actually rather easy to identify where the maximums and minimums are, as long as it's lined up pretty well with the good lines. But when you're given just a plain function, it's time to use derivatives. So here is a basic one. Trigonometry, sine of x. So I'll erase this. This one's actually going to get into a. Actually, I'll skip this one for now so we can get into the concept a bit later. Let's do 4 minus the square root of x. So f of x equals 4 minus the square root of x. The question is asking us, what is the absolute maximum, minimum? I'll just write it here. We'll reuse this for the questions. Local max and min. I'll just change color. Okay, so the question is, what is our absolute maximum? What is our absolute minimum? So for one, keeping it simple, we can actually visualize this on the graph pretty easily. So the parent function is square root of x, which we know on the graph is just starting at 0, going like that. And it just keeps going. Not a problem. So on this one, we have a big graph, a y-intercept at y equals 4. And instead of going up, it's going to go down, so it's just going to go like that. And on for forever. It's not going to end. So it goes towards infinity. So absolute maximum, absolute minimum. We can say that the maximum occurs at, this needs to be 0, 4, and the minimum does not exist. There is no minimum. And in terms of local maximum minimum, there is no point where it converges and then changes direction. We can actually apply the derivative of this. So it is also going to be does not exist and does not exist. Because there's no point at which it turns in which it's more than anything except for the endpoint. It's always going to keep going straight down to infinity. So that one was pretty easy, pretty simple. You didn't actually have to use the critical numbers for it because there weren't that many, actually. And it would have been a does not exist anyways. So let's get on to our next example. This one's actually going to have us use the critical numbers. It's going to be x cubed, or f of x equals x cubed, equals x cubed plus 6x squared minus, if I was not wrong, 63x, minus 63x. Okay, so how do we find the critical numbers? Well, all we have to do is solve the derivative for 0 and for where it doesn't exist. This one, conveniently, does not have any points where the derivative doesn't exist, so it's going to be pretty simple to find the critical numbers of. So that's just going to be, using our rules, 3x squared plus 12x minus 63. And now we just have to find the factors. So 3x squared plus 4x and 63, I think that's going to be 18. Double check. Nope. 12. 63 divided by 4. Yes, that's going to be 21. So minus 21. Do some quick factoring. That's going to come out with x plus 7 and x minus 3. So our zeros of the derivative, at least, are x equals negative 7 comma 3. And what does this mean? That means that on our graph, draw a quick graph here, x values 7 and 3, or negative 7 and 3, are going to be the points at which we have maximum and minimum. Not too hard. So now that we've found our critical numbers, it's as simple as that. And now when if we wanted to draw the graph, we would start getting into the second derivative, which would be the acceleration. But we can go with this and see which one is higher and which one is lower. So let's plug it back into the original equation. So 7 and 3, take them back up to here. I'm going to change color just to signify that we're not on the same problem anymore, on the second concept. So negative 7 cubed plus 6 times 7 squared minus 63 times 7, negative 7, sorry, is going to come out to be, plug in our calculator, negative 7 store x cubed plus 6x squared minus 63x. That's going to give us 392. So now let's do the same thing for x equals 3. That's going to give us negative 108. Easy, not too tough. And there we have it. We have the coordinates of our maximums and our minimums. Now we still don't actually know if they are maximums or minimums respectively. All we know is that they are points at which there is a maximum or minimum. So let's move on. Let's get into the trigonometry of it. So erase this. Let's start out simple. F of x equals sine of x. Now, the interesting thing about trigonometric functions is that they don't actually have maximums or minimums. The reason being is that they oscillate. When you have something that oscillates, goes up and down, it is always going to be approaching specific values, and so it's never going to have an absolute, if I'm not wrong. Yes, that's how it is. Actually, let me double check that. So, with this, we know that this is less than, so at x equals pi over 2, we don't actually have a maximum or a minimum. So if we have maximums and minimums, we can say confidently that we do not have an absolute maximum. We have an absolute minimum because less than or equal to at 0, and the local max and local min do not exist. Now let's make it a bit more complex. The next question asks 7 cosine f of x equals 7. Oh, that doesn't go there. 7 cosine x. And on the interval, what's the interval? Negative 3 pi over 2 x is equal, yep, 3 pi over 2. If we put this on a graph, we can see what cosine looks like. Cosine starts here, oh, that got really weird really fast. Okay, now what is the interval we have? Well, when cosine of 3 pi over 2 is equal to 0, if I'm not wrong. Cosine, yes, is equal to 0. So what we're looking at is a slice of a domain being this. The question, of course, is asking what are our minimums and our maximums. So if we look at it, we know that the endpoints are defined here because greater than or less than or equal to, or greater than or equal to and less than or equal to. So we don't have a problem there. And we can see that there are clearly differences on the curve. So, dissecting the function itself, 7 determines the magnitude of our our function, which means that it's not going to go beyond a value of 7. It's always going to be a magnitude of 7. So, as a result, actually I do this wrong. It's going to go below, it's going to go above, and the absolute minimum is going to be negative 7. And the highest is going to be 7, just based on the magnitude. It doesn't get much more complex than that. But if we wanted to find our using a critical number, what we would do is we would just take the derivative, which would be the derivative cosine is negative sine, so it would be negative 7 sine of x. And the values at which x, or sine of x, is equal to 0 is when the value of x is equal to 0. So, 0 or pi, 0 in or pi in, which would be telling us the n is essentially which repeat or iteration of the curve we're on, because it oscillates, so which oscillation we're on. Now it'll tell us that at 0 and pi we have reached our point. So we can plug these values back in, 0 and pi. So 7 cosine pi is going to be equal to 1, and 7 cosine of 0 is going to be equal to 1. So at x equals 1, let's see where it is. Oh, x equals 0, we're right here, and boom, that's a maximum. And over here, x equals pi, which is going to be this, we're at negative 7. So you can see how our critical numbers have helped us yet again to find what we need. So I think I'll just do one more example, and we will move on. Let's see. Let's do something difficult. Ooh, an absolute value. This one will be useful. So absolute values are interesting because you just want to find where they hit the absolute like lowest point. So let's take 8 minus 7x. So this function actually is a function comprised of two functions on different domains, where negative 7x plus 8 is on the domain where x is less than or equal to some value. And the other one is 7x minus 8, if I'm not wrong. It's the inverse for x is greater than or equal to that same squiggly value. And what we want to do is we want to find that squiggly value, where the absolute lowest point is. So we can just solve one of these. Is it 8/7? Yes. Either of these for its 0. So I can do 7x minus 8 equals 0. I'm going to give it 7x equals 8. That's going to be x equals 8 over 7. Or I can do negative 7x plus 8 equals 0, which is going to be negative 7x equals negative 8. And x equals negative 8 over negative 7, or 8/7 simplified. And so we get the exact same answer. And that is going to be on our graph looking something like this. And our x value right here is going to be 8/7. So it doesn't get much more complicated than that. And you can see how each of these is a different function, where the first one has a slope of negative 7 and the y-intercept is 8. This one has a positive slope of 8, but if you go back down here, the y-intercept is going to be negative 8. And that's how you mess with absolute value functions. So that's another aspect, but I really want to do a difficult problem just to review it. So let's find the critical numbers of this special function, where y minus 3, or f of x, equals y minus 3 over y squared minus 3y plus 9. Y squared minus 3y plus 9. Okay, so what do? Well, all we have to do is take the derivative and find what happens. So you remember the quotient rule is going to be f over g is derivative of that is going to be derivative of f times g minus f times derivative of g all over g squared. And we're going to end up with 1 times y squared minus 3y plus 9 minus y minus 3 times 2y minus 3. All of that over y squared minus 3y plus 9 squared. The truth is, we don't actually have to simplify it a ton, because to find the zeros where it's defined and where its actual zeros are, we just have to solve the 0 for the numerator and the denominator. Remember, if it's a 0 on the denominator, it's undefined. If it's a 0 on the numerator, it's going to be 0, regardless of what the opposite respective sides are. So let's just simplify the numerator first. The numerator is going to be y squared 3y plus 9 minus, I'm going to combine these, 2y squared minus 3y minus 6y plus 9. And we're going to move along. So y squared minus 2y squared is going to be negative y squared. So minus 3y, and that's going to flip the sign, so it's going to be 0y plus 6y. And then 9 minus 9, so plus 0. That's what we're going to get. So we can factor out a negative y, and we're left with y minus 6. And we get two values. We get negative 0 and 6. And coincidentally, these are two of the critical numbers. So now all I have to do is solve the denominator to find where it is, or where those critical numbers are. Remember, if the denominator does not have any zeros, then there are no critical numbers there. So denom, can you see me? Yes. Okay, so we actually don't have to factor out the square. We can just do y squared minus 3y plus 9 equals 0. So what are the factors of this? I actually don't think there are any, because the answer is eluding me. Let's see. Let's do the quadratic form. Actually, just plug in my calculator. Do it the fast way. So x squared minus 3. Good news, there is no 0. So this function is always going to be defined. So our two critical numbers are these, 0 and 6. There's no such thing as negative 0. And if you want to find the values of the absolute of the values of these maximum minimums, you just plug 0 and 6 back into the original equation. It's simple as that. And I believe that is it. Yep. So thanks for watching. Hope you enjoyed that. Bye.